Most people think of thermodynamics as the study of heat and temperature. And that's not wrong, but it's actually something much deeper than this. It is the study of what is and isn't possible in the universe. In physics, we often try to predict exactly what will happen in a given scenario. If we were to shoot a cannonball off a cliff, for example, we can calculate the path it will follow by writing out the forces and therefore calculating the velocity at each moment in time. We can do this easily because we have a well-defined object with a well-defined mass. But physics is rarely this simple. For example, a glass of water consists of around 10 to the power 23 water molecules. Here I've modelled just 100 of them as simple spheres. Each one has its own motion and kinetic energy. Now imagine trying to track every single one of them over time. Even for 100 particles, this quickly becomes complicated. But for 10 to the power 23 molecules, it's just incomprehensible. For comparison, there are estimated to be around 20 quadrillion ants on planet Earth, which is 2 times 10 to the 16. To match the number of molecules in just one glass of water, you'd need around 10 million Earths worth of ants that are all interacting constantly. And this is still a huge simplification. Real molecules don't behave like simple bouncing spheres. Their interactions are governed by quantum mechanics. So the true level of complexity is far beyond anything we could ever hope to calculate. But here's what's amazing. Even for systems as complex as this, we can still make extremely reliable predictions about what will happen overall. Not the exact details, like where every water molecule is, but the overall outcome. Imagine we have a warm cup of coffee in a cold room. If we were to measure the temperature of the coffee and the surrounding room over time, I'm sure you could guess that the coffee cools down. Not only that, we could imagine this happening for every cup of coffee that's ever been left in a colder room, over the entire course of history. But this is really interesting because every single cup of coffee contains a unique orientation of 10 to the 23 particles. Yet every time, we can predict with extremely high probability what will happen, at least in terms of some of the things we care about, like whether our coffee is going to remain warm. We have an incredibly complex system, and yet its overall behaviour is simple and predictable. So what's going on here? How can a system with an unimaginable amount of moving parts always evolve in such a simple way? Well, even though we can't predict everything exactly, it turns out that we can still say which overall changes are allowed and which are not. We call these changes, like changes in temperature, pressure, or volume, macroscopic changes. These are basically things that describe the system as a whole, and we can usually understand them on a human scale. Meanwhile, things like the momentum or kinetic energy of each tiny water molecule is a microscopic change which we cannot see or comprehend with the naked eye. We cannot predict all the microscopic changes that are happening within this cup of coffee, but we can predict the macroscopic changes. And this is incredibly powerful. This is the essence of thermodynamics. We're not predicting exactly what will happen, but we can rule out what cannot happen. And from this alone, we can predict the direction that the system will evolve in. For example, we never observe a warm coffee getting warmer in a cold environment. You probably think this is obvious, but it's actually not. After all, why couldn't energy go from the cold surroundings to heat up the warm coffee? In this scenario, energy would still be completely conserved. And this highlights another interesting point, which is how the laws of thermodynamics were originally discovered. In the 19th century, scientists didn't even know that atoms or molecules existed. These laws were built entirely from experiments, like observing how solids, liquids, and gases respond to heat. It was only later, with the development of atomic theory, that we began to understand why these laws work. This led to a deeper theory, known as statistical physics, which describes systems in terms of large numbers of particles. It then applies simple probability to predict what is most likely to happen. So overall, thermodynamics tells us what happens, while statistical physics explains why it happens. Thermodynamics is macroscopic, while statistical physics is microscopic. So in this series, our goal is to build the laws of thermodynamics from the ground up. Along the way, We will occasionally look at a microscopic picture as well, as, though it isn't essential, in my opinion, it really helps explain certain concepts. So let's quickly summarise what we've learnt in this video. Thermodynamics is a set of laws that tells us what can and cannot happen in nature, and in which direction physical processes occur. It is particularly useful for systems with enormous amounts of particles, like a glass of water, where tracking every detail is impossible. Instead of predicting exactly how each molecule moves, thermodynamics allows us to predict how the system as a whole will evolve. Thermodynamics is therefore a macroscopic theory, while statistical physics is a microscopic approach, describing systems in terms of particles and probabilities, and explaining why these thermodynamic laws work. So over the course of this series, we'll uncover all the laws of thermodynamics. But before doing that, we need to properly define what a few things are. Firstly, what even is temperature? Sure, we can measure it with a thermometer, and we know what a warm or cold temperature feels like. But what actually is it? What are we feeling? This is what we'll explore in the next lecture. By the way, if you enjoyed this video and want to practice the topics covered in it, try out the Decipher Physics app and websites, which have interactive lessons and practice questions for this video and several others. It's completely free to use. Thanks for watching.